Okay, so this is Stewart's calculus. Differential and integral. Stewart's calculus. Chapter 1, functions and limits. Section 1, 4 ways to represent a function, and other topics. But our first objective is that the student would be familiar with the 4 ways to represent a function. Functions arise whenever one quantity depends on another in a particular way. Consider the following 4 situations. In each of them, we will see that one quantity, one variable, depends on another. The area A of a circle depends on the radius r of the circle. Right? Increase the radius, you increase the area. You decrease the radius, you decrease the area. The rule that connects r and A is given by the equation A equals pi r squared. With each positive number r, there is associated one value of A, and we say that A is a function of r. The human population of the world P depends on the time T. So we have a table that shows how one quantity depends on another. The table gives estimates of the world population P of T at time T for certain years. For instance, P of 1950 is 2,560,000,000. But for each value of the time T, there's a corresponding value of P. And we say that P is a function of T. The population depends on time, the year. Here's another function. The cost C of mailing a large envelope depends on the weight W of the envelope. How much does it cost? Depends on the weight. Although there is no simple formula that connects W and C, the post office has a rule for determining C when W is known. I think it is actually a linear function, so I think it is actually simple, but whatever it is, there is definitely a function there. The vertical acceleration A of the ground, as measured by a seismograph during an earthquake, is a function of the elapsed time T. It's a function of the elapsed time T. Here's a figure that's showing a graph generated by seismic activity during the Northridge earthquake that shook Los Angeles in 1994. For a given value of T, the graph provides a corresponding value of A, where A is vertical ground acceleration. Here's a definition. A function is a rule. We are not to think that a function is a set of ordered pairs. It's a rule. We could say it's a correspondence. Function f is a rule that assigns to each element x in a set D exactly 1. Those are the important words in this definition. Exactly 1 element called f of x in a set E. I don't know why we wouldn't call that set R, but we'll call it E. We usually consider functions for which the sets D and E are sets of real numbers. The set D is called the domain of the function. Set of x values. The number f of x is the value of f at x. So f is the value when x is the input and is read f of x. It's not f times x. The range of f is the set of all possible values of f of x as x varies throughout the domain. And of course that f of x there is the y. So the range is actually the set of y values. A symbol that represents an arbitrary number in the domain of a function f is called an independent variable. A symbol that represents a number in the range of f is called a dependent variable. And of course that is the y variable. Of course we could use different letters for it. Any letter we want, really, except x if we want to avoid confusion. In example A, for instance, r is the independent variable and a is the dependent variable. R is independent, the radius of the circle is independent, the radius gets to be whatever it wants to be, but then a must follow, it's dependent. The area just is what it is after r, the radius, has decided what it wants to be. It's helpful to think of a function as a machine. So there's the old function machine. You've got an x, it's some number, it goes into the function machine. The function machine does something with it, spits out exactly one number, f of x. If x is in the domain of a function f, then when x enters the machine, it's accepted as an input, and the machine produces an output f of x according to the rule of the function. Thus we can think of the domain as the set of all possible inputs, the range as a set of all possible outputs. A function then is a rule that assigns to each input exactly one output. Another way to picture a function is by an arrow diagram, as in figure 3. So we've seen table, we've seen machine, we've seen a graph. Here's an arrow diagram. And you've got domain elements over on the left in that region on the left. Each one is mapped to f of whatever that is over on the right in the range. Each arrow connects an element of D to an element of E. The arrow indicates that f of x is associated with x. F of A is associated with A, and so on. The most common method for visualizing a function is its graph. If f is a function with domain D, then its graph, now that's what a set is. A function is not a set, the graph is a set. The set of ordered pairs. The set of all ordered pairs x f of x such that x is an element of the set D. In other words, the graph of f consists of all points x, y in the coordinate plane, the xy plane, such that y equals f of x, and x is in the domain of f. The graph of a function f gives us a useful picture of the behavior or life history of a function. Since the y-coordinate of any point xy on the graph is y equals f of x, we can read the value of f of x from the graph as being the height of the graph above the point x. So that's what f of x is. F of x is the height of the graph. It's really the y, isn't it? The graph of f also allows us to picture the domain of f on the x-axis and its range on the y-axis as in figure 5. Sometimes we draw a box around the graph when we're asked for the domain and range. This picture here relates the graph to an interval on the x-axis and an interval on the y-axis. The graph of a function f is shown in figure 6. A. Find the values of f of 1 and f of 5. And B. What are the domain and range of f? Okay, so in other words, when x is 1, what is y? And when x is 5, what is y? And those two values of y will be the two answers in part A. And then we're going to do the domain and range question, which again, as we said a moment ago, it's helpful to think of there being a box around the graph. So to do the domain and range question, we're going to draw a box around the graph, and it's going to be seen that the domain of the function roughly is left edge of the box to the right edge of the box, and the range will be top of the box to the bottom of the box to the top of the box. Okay, so part A, what is f of 1 and what is f of 5, I believe the other one was. We see that the point 1, 3 lies on the graph of f. And we ask, what is y when x is 1? Well, when x is 1, y is 3. So the value of f at 1 is f of 1 equals 3. So that's the first answer right there. When x equals 5, what is y? 2, 3, 4, 5. Well, it's hard to tell exactly what it is. We know it's between 0 and -1. Between -1 and 0. When x is 5, the graph lies about 0.7 of a unit below the x-axis. So we estimate that f of 5 is approximately equal to -0.7. When x is 5, y is approximately equal to -0.7. Part B, we see that f of x is defined when x is between 0 and 7. So the domain of f is the closed interval. Closed interval, it includes its endpoints, 0 to 7. And again, we can also see that from the box that we could draw around the graph, which has a left edge at 0 and a right edge at 7. And we will draw look at the bottom of the box and the top of the box to answer the range question. Notice that f takes on all values from -2 to 4. -2 to 4. So the range of f is a set of all y such that y is between -2 and 4 inclusive. That is the closed interval, -2 to 4. Right? 4, that's part of the range. That's part of the set of y values because there's the 0.24 right on the graph there. So 4, we see that in the ordered pair. It's a y value. It is included in the range, so that's why we have the square bracket and not the round parenthesis. Likewise, -2. And so we see another way to represent a function. There are 4 possible ways to represent a function. Verbally, that is by a description in words, right? We could just say in words that the area of a circle depends on its radius. Numerically, by a table of values. Sometimes we say tabularly, which is actually quite a bit more fun to say. Tabularly. Visually, by a graph. Sometimes we call that graphically. Algebraically, by an explicit formula. So those are the 4 ways to represent functions, the 4 main ways. There are minor ways like arrow diagram. Maybe that falls under visually. Example 4. When you turn on a hot water faucet, the temperature T of the water depends on how long the water has been running. So temperature big T depends on time little t. Draw a rough graph of T, big T, the temperature, as a function of the time little t that has elapsed since the faucet was turned on. The initial temperature of the running water is close to room temperature because the water has been sitting in the pipes. It has not been heated up yet. When the water from the hot water tank starts flowing from the faucet, big T, the temperature, increases quickly. So we're going to see an increase in the function. It's going to go uphill as we read from left to right. In the next phase, big T, the temperature, is constant at the temperature of the heated water in the tank. So we're going to get something like a horizontal line for that portion of the domain. Then the tank is going to drain. Temperature decreases to the temperature of the water supply. And so put it all together and you've got a graph like that. Okay, so as we read from left to right, that is, as time goes on, the temperature of the water will increase from room temperature to hot. Then as long as we have hot water, it'll continue to run hot. But then as we run out of hot water, we have a rapid decrease in the temperature, big T. And then once we're all out of hot water, we have something like a constant function with a horizontal graph the rest of the time we want to run that water. And of course it's at a much lower temperature than when we had hot water. The graph of a function is a curve in the xy plane. Even if it's a line, we still call it a curve. But the question arises, which curves in the xy plane are graphs of functions? And so to answer that question, we have the old vertical line test. The curve in the xy plane is the graph of a function x if and only if. Okay, so function, that's the question. When does it function? Well, if and only if no vertical line intersects the curve more than once. So the no vertical line, if no vertical line intersects the curve more than once, that is, no matter where we draw it, it doesn't intersect the curve more than once, then we have the graph of a function. That's what we see in the picture on the left. So we could draw a vertical line anywhere. The y-axis itself also serves as such a line. And we would only have one point of intersection with the graph. If each vertical line x equals a, so like that pink line, intersects a curve only once at AB, then exactly one functional value is defined by f of a equals b. There's only one b there, okay? There's only one output. There's only one y value when the x value is a. But if a line x equals a intersects the curve twice, as happens over here on the right, then the curve can't represent a function because a function can't assign two different values to a. Remember, a function is a rule that assigns to each element x of the domain exactly one element f of x in the range. But here it's not exactly 1, it's 2, and so that relation is not a function. We could look at a sideways parabola. Here's a curve in the plane. It relates x and y, and that thing's going to fail the vertical line test. We can see the y-axis does exactly that. And so we don't have the graph of a function. The parabola, however, does contain the graphs of two functions of x. If we consider just the top half of the parabola, that would be the graph of a function, or just the bottom half of the parabola, that could represent a function. If you were to solve for y in that equation that we had, x equals y squared minus 2, okay, so add 2 to both sides, and y squared equals x plus 2, then take a square root of both sides, and of course when you take a square root of both sides, one side is plus or minus top half of the parabola, bottom half of the parabola. Thus the upper and lower halves of the parabola are graphs of actual functions, but the thing is you have two of them. So we could not say this thing here is or represents a function. It's actually two functions, but as considered as one, it is not a function. So top half, square root of x plus 2, bottom half, call it g of x, equals the negative of the square root of x plus 2. Both of which individually, again, pass the vertical line test, but separately, put together, considered as one relation, not a function. Okay, so we observe that if we reverse the roles of x and y, remember something about that, reversing the roles of x and y, the inverse of a function, then the equation x equals h of y equals y squared minus 2 does define x as a function of y. That is after the reverse, not in this sense. In this one here, which is the one we've already seen, the sideways parabola, y is the independent variable and x is the dependent variable. But if we switch it, then x is the independent variable, y is the dependent variable, and the parabola would now appear as the graph of a function h, right? Because then we'd have y equals x squared, and in that case we would have y equals x squared minus 2. We would have a graph that looks like this, something which passes the vertical line test, and now we have a function.